everyone, and welcome to our lecture on noncovalent forces. We'll be talking about the different types of bonds that you should know, as well as touching on solubility today as well. So just to give an overview of noncovalent forces, they are intermolecular attractive forces that affect the molecular organization and physical properties of organic molecules. And the stronger the attraction, the more energy that is needed to break the attraction between the molecules. So, for example, here I have some molecules of acetone, and if we were to compare a non-covalent force to a covalent force, covalent forces are intramolecular, meaning it's within the molecule itself. So this would be an example of a covalent force, this force within the molecule, whereas an intermolecular force would be something that's between two separate molecules here. And there are several types of non-covalent forces we're going to be going over, and this is them listed below here in terms of the strongest to the weakest. So the strongest is the ionic bond, which is stronger than hydrogen bonding, which is stronger than dipole, and then London forces are the weakest. So the first is an ionic bond, and these are electrostatic permanent bonds, and this has more electronegativity than a covalent bond. So ionic bonds are something like when you have lithium bonded to a fluorine, for example. So you have this transfer of electrons in order to form anions and cations. And the reason this electron transfer occurs has to do with the number of electrons in the shells. So in lithium, for example, we have just this one electron right here, and lithium would prefer to have a full valence shell. And so it'll just transfer its electron over to the fluorine. That electron will end up over here. Now fluorine has 8 valence electrons and lithium has 2, and they both have full shells, and that's the basis behind why an ionic bond forms, and it forms something like lithium fluoride. And as a result, you have this Li plus and this F minus that forms to these cations and anions. And these ionic bonds tend to be pretty strong, actually, just due to the fact that these electrons have been transferred over. So the next thing is a hydrogen bond, and these are also electrostatic forces. They are particularly important in DNA and in the proteins of our body. So if you see the DNA and the protein videos on the website, you'll see that we talk a lot about hydrogen bonds in terms of the stability of these biological molecules. So for a hydrogen bond, there's 2 major things you should know. The first is to be able to recognize a hydrogen bond acceptor and also to recognize a hydrogen bond donor. So an H-bond acceptor is usually a molecule that has some highly electronegative atom that can accept the proton or the hydrogen in the hydrogen bond. So if we were to look at this molecule here, we have oxygen, which would be the hydrogen bond acceptor. And this is very electronegative. So there would be a hydrogen bond that forms between oxygen and the hydrogen bond donor. So in this case, the hydrogen bond donor would be this molecule. And in a hydrogen bond donor, you would look for a hydrogen that can be donated to the hydrogen bond, and usually this hydrogen is attached to a highly electronegative atom, usually an oxygen, could also be a nitrogen or a fluorine, oftentimes. So a hydrogen bond donor has a very, very electronegative bond, and this enables the hydrogen to be able to form this H bond with the H bond acceptor. So here's our H bond here. Okay? And just to give a little bit more context about this, since this oxygen is very electronegative, this H here has a really strong delta plus or positive partial charge, whereas this oxygen here has a really strong delta minus or negative charge. So it's pulling these electrons towards itself away from the hydrogen, and this kind of helps facilitate that hydrogen bond formation. In hydrogen bonds, we also see them, as I mentioned, in proteins. So let's take a look at these amino acids here. Here I have threonine, and here I have valine. So, let's take a look and decide whether or not, based on the structure of these molecules, whether or not they can form hydrogen bonds. And the important thing here is to look at the side chains because everything else in the molecule is the same. So we're really looking at this part right here and this part right here of the molecules. So let's just focus on the parts I've circled and decide whether or not this molecule can hydrogen bond, and whether or not, based on the side chains, it would compose the molecule core or the molecule surface. So remember, in hydrogen bonding, we look for a hydrogen bond donor or a hydrogen bond acceptor. And here we see we have an oxygen and threonine. And this oxygen means that this can be a hydrogen bond donor or a hydrogen bond acceptor if we were to have multiple molecules of threonine around. So yes, this can hydrogen bond. And something to remember in proteins is that when you're having a protein that folds within itself, it kind of folds together like this, you have an aqueous environment that surrounds it, and this aqueous environment is polar. So when you have a molecule that can hydrogen bond, this means that the molecule contains polar atoms, and this means that it can interact with the aqueous environment. And so a molecule like threonine would be in the molecular core, or would be in the molecular surface, meaning that it can interact with this aqueous environment outside of it. Let's take a look at valine. So the hydrogen bonds here, can we see that? And looking at this structure here, no, we cannot do hydrogen bonds. And that's because these hydrogens are attached to carbons, which are not that highly electronegative, and they're not enough to create a strong partial positive charge on the hydrogen in order to facilitate bonding of hydrogens. So no, it cannot form hydrogen bonds with other valine molecules. And since these methyl groups are nonpolar, if we were to put this in an aqueous environment, such as something like in the body, we would find that this molecule would orient itself into the core of the protein because of the fact that it's nonpolar and wants to avoid the polar environment outside. And if you're not sure what I'm referring to, this all is in reference to the protein lecture, which discusses the orientations of molecules in protein folding, as well as the effect of the side chains on their protein folding. The next thing you should know is a dipole-dipole. So dipole-dipole bonding has to do with these partial positive and partial negative charges, and again, it's an electrostatic force, meaning these opposite charges are attracting each other. So when you have something like HCl, chlorine is a highly electronegative atom, so it has a really strong partial negative charge. And since it's pulling all of these electrons towards itself, hydrogen then has a very strong partial positive charge. And similarly, in this molecule, we have this same thing. So when you have two HCl molecules interacting together, you get a dipole-dipole force between the atom with the partial positive charge and the atom with the partial negative charge. And this actually more often happens when these molecules get very close in proximity to each other. It's not as strong as an ionic bond or a hydrogen bond, but again, it has to do with these, of course, dipoles being formed. And then the last type that we're going to really talk about today is London forces, and these are also electrostatic, meaning opposite forces are attracting, but unlike the others which were permanent, these are temporary, meaning that this force doesn't necessarily always exist, and you'll see why in a moment. And this actually has to do with the polarizability of the molecule. So polarizability refers to the movements of the electron cloud, and this kind of spontaneous movement forms these dipoles within the molecule. And so let's take a look at this drawing down here. We have a sample molecule here, and you can see that there's a delta minus and a delta plus, and here's the nucleus. So if you imagine all of the electrons just kind of like moving towards one side of the molecule, this electron cloud kind of distorts, and this creates this uneven distribution of electrons and helium, as opposed to something like this, which does not have any dipole in it. And as a result of these electrons kind of all moving over to one side of the molecule, you get this delta plus here, where there's a deficiency of electrons. And as a result of this random, instantaneous distribution of electrons, this causes the atom next to it to also have its electron cloud be distorted. So now, here we have this molecule again. The electrons are moving into one side. This creates a partial positive charge, and since opposites attract, now the electrons in the adjacent atom are getting pulled towards this positive charge, and now we have another dipole that's being formed. So the difference between these dipoles is one is instantaneous and the other one is induced on a neighboring atom. So to sum it up, when you have an uneven electron distribution, this leads to an instantaneous dipole. I'm just going to abbreviate that here. Instantaneous dipole, which is this uneven distribution of electrons, and this leads to an induced dipole in a neighboring molecule, and then you have this interaction here between these atoms. So an important thing to know about London forces is that even though they're the weakest, if you have a lot of them together, kind of teaming up together, this can actually create a very, very strong force of attraction. So if you have a large surface area of London forces, this leads to stronger forces of attraction. So if you had a molecule like hexane here, and you had many, many, many hexane molecules just interacting together, you would find that this actually has a stronger intermolecular noncovalent force than something like this, which does not have as much surface area. Less places for them to have contact with each other, and therefore you have this weaker force of attraction here. So as a result, when you have a molecule with a large surface area like this compared to this would have a higher boiling point. So I'm just going to briefly go over the other noncovalent forces. They're not as integral to understanding noncovalent forces as the four that we mentioned before, but they're important to biologically as well. So you have ion-dipole interactions where you have this ion here. In this case, we have a sodium cation interacting with a molecule that has a dipole in it, as you can see by these partial charges. And so they kind of orient themselves around this ion here, and you have this positive charge that's interacting with these partial negative charges, since these opposite molecules or opposite charges attract. And then we have something called pi stacking and cation-pi interactions. And this is important in things like DNA, where you have basically a lot of aromatic molecules stacked on top of each other, and there's interactions between them. And so in pi stacking, you have these aromatic rings that kind of get attracted to each other, and they have pi clouds and pi electrons that interact. And the last thing I want to go over today is solubility. The most important thing to remember with solubility is that like dissolves like. So that means that if you have a polar solvent, you want a polar solute. If you have a nonpolar solvent, you'll have a nonpolar solute that can dissolve in it. So let's consider something like acetone. And if you say we were to mix acetone with water in a mixture, like in a flask, for example, we would find that this is soluble. So acetone is soluble in water. And the reason for this is because acetone is a polar molecule, and water, as we know, is also polar. Now let's take a look at benzene, for example. So this would be considered insoluble in water due to the fact that it's extremely nonpolar. It has all of these carbons and hydrogens. There's not really any electronegative atoms. Benzene is nonpolar, so in a solvent that is polar, like water, it would not dissolve, since there are different types of molecules. And just to provide a little bit more context, in solubility, when you have something like NaCl dissolved in water, the water molecules, since this is a little bit different, this has to do more with ions, but these ions, which are positive and negatively charged, can interact with the dipoles of the water, and this allows these partial positive and negative charges to interact with each other, and that's how it pulls the sodium chloride pieces apart from each other. So it pulls, so the water surrounds each of these individual atoms in NaCl and just kind of surrounds it and pulls it away, and that's how it dissolves. So that's all you need to know. Thank you for listening.